We're converting to moles, and what do we get?
0.08.
0.085. We'll go one more digit.
Um,
0.0855 moles. So 0.0855 moles divided by, now this is 95 milliliters. I'm going to convert it to liters really here. 0.05 liters. And this gives us a molarity, right? What you come up with, Daisy?
0.8, well, 0.90,
3 CPs.
0.
0.900?
Yeah.
So that's a molarity. And remember, okay, so that's our molarity of what? The saline, right? Is salt ionized? Well, the answer is yes. So in this case, I am also going to need my ionization factor. Okay, so let's look at how this goes. Molarity, what is that? 0.900 moles per liter times R. Which R should we use? I hope you haven't used R for a while. What is R? Okay, 0.0826. Remember what the units are? Atmospheres. Yeah, I didn't say what temperature, did I? What temperature should we use?
Standard
Standard.
or room temperature?
What's that?
Would you do standard or room temperature?
We could do standard or room temperature. Where is this important? Where is this important? What were we talking about before?
Cell,
I know the cell.
probably body temperature,
Right, which is
37 degrees Celsius.
37 degrees Celsius. So is that the temperature we use? Why not, Cyrus?
Don't we use 273, right?
Not, well, you're on the right track. What is the 273?
That's the Kelvin baseline. Kelvin.
Right, so I need to convert it to Kelvin. So this is gonna be 310 Kelvin. Okay. So, okay, well, look, our moles cancel, our liters cancel, our Kelvin cancel, giving me atmosphere. How many atmospheres?
Point 2.9.
That is why the cell ruptured. It's a lot of pressure. Now, it does go down some once you get the inner part of the cell. As the pressure, as the concentration gets diluted inside, but it still puts a lot of pressure. Yes.
Are we multiplying the ionization number?
Oh, yeah, we forgot ionization. Wow, okay. Because this is 2. So that gives us what? 5.8?
Yeah.
Okay. So this is why if you, maybe how many are going into some type of medical field or another? Lots of you. Okay. Say lots of you are, but this is why it's so important that IVs are kept at a fairly constant concentration. Generally, they just don't take, oh, here I have an IV bag and I have some solid medicine. Let me just throw it in there. Usually they dissolve the medicine into some IV solution and then they add it to the larger IV so that they keep a fairly constant tonicity, which is, in other words, they want it to be the same pressure as the cell. So we have hypotonic. So if I put a cell in pure water, it would be hypotonic. Okay. If I put a cell in the solution that's the same as what is inside, that's isotonic. And then what's the other possibility?
Hypotonic.
Right, so if I put it in saturated salt water, it would be hypotonic. And basically the water goes out of the cell and the cell kind of shrivels up. Also a bad problem for the cell. What's that?
Is it hypotonic on it? Is it hypo?
Hyper. Okay.
Yeah.
Starting off the semester really good. Okay, yeah, keep catching my mistakes. So this all sounds really good, right? I could do calculations for vapor pressure, freezing point, boiling point, and I could use this and fairly easily calculate the osmotic pressure. But I'm gonna do something fun. Now that you have all this down, you guys gotta keep up. I can just erase stuff really quick. Unless I feel. And in case you're wondering, why am I only writing on this side of the board? I'm attempting to record this. We'll see if it actually works. And if you never ever see this recording show up on Canvas, then you will know, oh, okay. And in case you're wondering, yes, I recorded in this room during COVID a whole lot of times. And they have reset our system about 5 different times, and we're now using a different program. Microsoft Teams. You guys like Microsoft Teams? No, neither do I. Guess which program we're using?
Microsoft Teams.
Microsoft Teams. Okay. So anyway, let's do this. Okay. So let's take we should take a solution of a different solvent. So if we go to the table in your book in chapter 11, I love the online book, but I also don't love it. I'd rather just open it. So table 11.2, and we have several different solvents listed here, but I think we're going to use benzene. Okay. Okay. So benzene has a freezing point of 5.5 degrees Celsius and a KF (5.12 degrees Celsius per mole). Okay. Yeah. We'll use that. Okay. We're going to call it 5.50 degrees Celsius, but I'm being more precise than the book is on this. I think it might be 5.51, but we're going to use 5.50 so we can get three significant figures on this particular calculation. And if I dissolve, so let's say I have 100. And I dissolve 2.14 grams of solute in that benzene. Okay. And when I do that, I measure the freezing point. To be 2.16 degrees Celsius. What's the molar mass of this solute? Now, here's the thing. If the solvent is not water, we're going to use I. So we will not work with anything that ionizes in any solvent except for water. So if the solvent's not water, don't worry about the ionization factor. And that will be true for everything that we use in this class. Please note that doesn't mean it counts for everything, just that we were going to limit our non-aqueous solvents to things that do not ionize. Okay? Where would we start? How do we start this problem? Repeat that for a minute. See if you can figure out where to start this problem.
Balance.
Are we trying to find molar?
Well, so this is a solute, right? Do we know what the solute is?
No.
No. Find its molar mass. You know, generally we find molar mass by adding stuff up on the periodic table, but how did we ever come up with molar masses to begin with? Well, this is one of the ways that we can find the molar mass of a substance. What are the units for molar mass? Grams per mole. Okay. How many grams of solute do we have? 1.4. How many moles of solute do we have?
Can we just say one?
We could, but that would be wrong. Well, I don't know. I am guessing it's less than 1 mole. What do they do to this stuff?
Frozen.
I froze it, right? What is freezing point? Oh, yeah, I'll just say it. What is freezing point? It's one of our colligative properties, right? We have an equation that goes with it.
Yeah.
What is that equation?
AF times molality times ionization.
What does that equal to? Delta T is equal to KF times molality. Do we need to worry about I in this case?
No, that's one.
Yeah. Okay, so can I find delta T? How do I find delta T?
Sure.
Okay, so I subtract the two crazy points. Now, remember, my delta T is actually going to be, ooh, what is it? 2.96, is that right?
Yeah.
Now, really, we should put a negative here and a negative here. And I'm gonna do this, because that's the way it should be, even though our book says, oh, delta T is 2.96. Well, no, it went down, so it's a negative. And that's equal to KF, right? Which is negative 5.12 degrees Celsius per mole times our molality. We find our molality. Dr. Mel, what did we come up with for the molality?
0.570.
And what is molality? I asked this because I know I messed up when I wrote it on. What is the actual thing? It is moles of solute.
So
We know how moles of solute. We know our kilograms of solvent.
Yeah.
Yes, if we can do a conversion, because I did 100 grams of benzene. So this is equal to moles of solute over kilograms of solvent. Right? So I have 0.0578 moles of solute, right? Can I find the molar mass? What are the units per molar mass?
grams per mole.
Grams per mole. Do I have grams of solute?
Yes.
Do I have moles of solute?
Yes.
Oh, wow. 2.14 grams over 0.05. Thank you.
.0 grams per mole.
Sounds simple enough, right? Okay. Now, I could use any of the four colligative properties to find the molar mass of something. Okay. I would just need to have the mass of it, and I can find moles from any of the colligative properties. So you should be able to do that with any of the colligative properties. Okay. Now, there's one more thing that we're going to cover in chapter 11 that's really important. Actually, a couple, but one that's really important. And in this case, a guy by the name of Van Hoff was studying these, and he found that when he did the calculation for the freezing point, of solutions, he found that if you use, you would expect I equals 2, right? But if you actually measured the freezing point, he often found that you would have I equals like 1.96. Okay, so if you were in a lab and expected to get 2 and you got 1.96, what would you say? Okay, I could say either some of them didn't ionize, or I am just in the first year chemistry class and I'm not very good. So maybe that's okay. But as he did more and more calculations, he found out that he was slightly off. So instead of using the ionization factor, he said, well, I'm going to experimentally find this factor. And because it doesn't come out what I expect, I'm going to call it the Van Hoff factor. Okay. And the Van Hoff factor is the factor that he put in to explain why things weren't coming up with what he expected. And as he increased the temperature, or not the temperature, as he increased the concentration, the I would go down to like 1.92 or even farther than that. Now, I really think that whenever my experiments don't work out, I should be able to add the overlay factor, right? And just make a correction. Well, we can't do that. In this class, unless you're specifically given a Van Hoff factor, we're going to use just the ionization factor. But don't worry about that. It can work. Okay? Sounds easy enough, right? But why would it do that? And what did you say? Some of them what?
Some of them didn't have an ionization factor, so some of them didn't break apart.
Okay. So there's actually Debye and Huckel, two different guys, came up with a theory. And they said, well, sometimes in a really dilute solution, your ions are going to be far apart. But as you get a higher and higher concentration of solution, even though I have a sodium ion surrounded by lots of waters, and I have a fluoride surrounded by lots of waters, sometimes in higher concentrations, those two will stick together and act as one ion or as one particle. Okay. And the higher concentration, the more of them stick together. That's why your Van Hoff factor goes down as you go. Now, we're not going to actually worry about doing the Debye-Huckel calculations to figure out what that is. But I do want you to know that if we go in experimentally under really high concentrations, our ionization factor will not be quite what we expect. Okay. And hopefully one of you guys will be successful enough to have your own error named after you. So, wouldn't it be cool if there was like a maybe a Martin factor because you made a mistake, but you figured out it's not a mistake. I was actually doing it right. Something just isn't working out right. And I can just make a name for the correction instead of actually figuring out what it is. Yeah. All right, so it doesn't work out that, but we can do these calculations. So this is chapter 11. There's a couple more things, but I'm going to wait till Wednesday to go through those last couple details on chapter 11. And then we're going to begin chapter 12 as well. And I know the lab we're doing this week, actually, I'm going to let you guys decide. Would you rather put the titration off for a week and do a freezing point lab this week? Or should we do the titration this week and the freezing point next week, after you've done all the problems.
Should do titrations.
Let's do the titration this week. Okay. That's okay. Titrations are fine. So we'll do a titration this week. We'll have a lab where we do the freezing point, and then we have a lab, because it's gonna take us a couple weeks to learn the kinetics. And then we'll have a lab on the kinetics. How's that sound? Okay. So with that, I think because of the weather and as many people who are gone, I don't want to cover too much. Again, I have it on video, but we'll see how that works. So I will see you guys. Yeah.